Winter. I'm an astrophysicist here at the Harvard-Smithsonian Center for Astrophysics. I'll try to get us out in time for lunch today. I'll just give a really quick presentation of some of the things I do. I actually got my PhD by doing extremely complicated magnetohydrodynamics, and I could have shown you 20 slides of equations, but instead I decided to focus on pretty pictures, right? So, first pretty picture. Number one, the sun. This is what I study, right? So I love studying the sun. It's really easy to be able to talk to people why the sun is important, why you do all these things. But the thing I always get is, oh, why do you study the sun? Listen, we see it most days, not today, obviously, but most days, you know, we get to see the sun, and it's just this kind of boring yellow round sphere, right? So what's so exciting about this? I'm like, yes, but I got this image just a few minutes ago. This is from today. This is nearly live. Still, people don't get as excited as the sun as I do. And why is that? And that's because we're used to seeing the sun in a particular way. We're used to seeing the sun in what we call visible light, right? Visible light, that's the light we can see with our eyes. We've talked a lot today about different forms of light that we can't see with our eyes, infrared, radar, all these different things. I'm going to talk about some other forms of light that we can't see with our eyes. And just as with everything else that you take for granted, all of a sudden it becomes exciting if you look at it in a whole new light. So, is the sun boring? Well, sometimes it can have these little spots on it. Oh, but wait, if we start looking at the sun, not just in the visible light, but in other wavelengths in light, and I'm going to use the term wavelengths a lot, and when I say wavelengths, I just mean a very specific color of light. But when we look at the sun and all these different wavelengths of light, right? All these images were taken at the exact same time, but we see that the sun looks very different in all of these different wavelengths, right? So this is the exact same time, but why do things seem so different? And that's because we're looking at different layers of the sun. So this layer of the sun we often call the surface of the sun, or the photosphere. We call it the photosphere, or the light sphere, because that is the part of the sun that we can see with our eyes. This is a very dense layer of the atmosphere. We can't really see, we can't really penetrate it unless we use some special techniques that are like sonar, and they're called helioseismology. But all of this stuff that you see here, all of this structure, all of these cool things going on, that's actually happening above the photosphere, right? And that's like the outer atmosphere. It's much thinner. It's not as dense as the photosphere of the sun. And we call this the corona of the sun. And you can see these bright features, right, in it, and they appear differently as they pass through all these different pass bands, right? So, in order to get a handle on what's going on, we need to look at the sun not just in the visible light that we're used to, but in all these different wavelengths of light. Now, there's a key problem, right? And it's really annoying, because all of these wavelengths here that you see are extreme ultraviolet light. Right? So we've talked about different wavelengths of light. We talked about infrared. When we talk about extreme ultraviolet light, everybody knows UV light, right? You can't see it with your eyes, but how do you know it's there? Sunburn. You get sunburn. So you can feel its effects, but you can't actually see it. Another wavelength of light is X-rays, right? Can you see X-rays with your eyes? No. How do you know it's there, though? How do you know it exists?
You observe its effects.
Say again?
You observe its effects.
You can observe its effects. When do you usually observe its effects? Yeah. When you go to the dentist, when you go to the doctor, right? They use it because it passes through your skin, but it has a little bit harder time passing through your bones. So this extreme ultraviolet light is in between ultraviolet light, what gives you a sunburn, suntan, and X-rays, not quite as powerful as X-rays that your doctors use. So it's in between. The problem is, the vexing problem for us is that we have this very thick protective atmosphere, right, that protects us from this EUV light. If it didn't, right, EUV light would come down, we could be able to build telescopes to actually image the sun like this directly, but there wouldn't be anybody around to build the telescopes because you think a suntan is bad. The type of cancers that you get from the extreme ultraviolet light exposure would be super bad. And there probably wouldn't be any life here to actually build those telescopes. So I guess it's a good thing that we've got a protective atmosphere. I'll give you that. So, what do? Well, you build satellites, right? And so this is a satellite called the Solar Dynamics Observatory. It's one of NASA's grand observatories. It is the flagship of the Living with the Star initiative. And we here at the Center for Astrophysics built a series of telescopes on it. There are actually 3 different instrument packages on the satellite itself. And I'll let this loop. There we go. So we built these 4 telescopes right here. They're called the Atmospheric Imaging Assembly, but since this is NASA, nobody calls it the Atmospheric Imaging Assembly. We use the acronym, and that's AIA. And with these different telescopes, we actually designed them so that there's a mirror and back, right, that reflects light. But that mirror is sliced in half, so there's 2 parts, and then we layer that mirror with a coating, right, over and over and over again. Those coatings are only a few atoms thick each, right? Because you can't reflect extreme ultraviolet light with a normal mirror like you've got in your bathroom. You can't actually use lenses to concentrate it. So you have to use these special quantum mechanical properties that come about when you layer things a few atoms thick, right? That's a process that we actually innovated here at the Center for Astrophysics. It's now used to make computer chips for your phones. So now we've got these telescopes, right? And the reason why we split the mirrors in half is so that we could put different coatings on each half. So with 4 different telescopes, we can actually image over 8 different wavelengths, specific colors of light. And this is the sun this morning, right? So I just downloaded these images from the satellite before I gave my talk today. So this is fresh off the press. You may be the first people in the world to see these. Congratulations. So what we're looking at is the sun and just regular old boring visible light, right? And then we're looking at all these different wavelengths, and then this is something even more special. I'll talk about that a little bit. So what do these different wavelengths talk about? Well, a previous speaker talked about how a spectra, right, that comes from atoms is like a barcode, right? It is a unique fingerprint. Well, something that they didn't mention is that that barcode actually changes depending on the temperature of the stuff that you're in. So not only can you tell what material you're looking at, you can tell what temperature it's looking at. And each one of these different images, right, these different colors of light, are actually representing a different temperature of the sun, right? So we got about 1 million here, we got about 2 million here, got about 5 million here, and we can have about 10 million there, right? 10 million, right? That's Kelvin, right? That's what scientists use because we're sensible. We don't use silly things like Fahrenheit. So if you want to do the conversion to Fahrenheit, it doesn't really matter because 1 million degrees is still 1 million degrees. It's like super hot. In fact, to give you an idea of how hot it is, right? This image, this image, this image, and this image is all using the same element it's all focused on the same element, right? Anybody want to guess what element we're looking at these different temperatures? You, right there. Oh, that's such a great guess. Why'd you guess hydrogen?
Just because stars have large amounts of hydrogen.
Yes, stars have large amounts. That's a fantastic guess. You're wrong. You. Helium. That's a great guess. Why'd you guess helium?
Because that's also stars.
Yes. Right. Stars are mostly hydrogen and helium. Thank you so much, you two, for making a perfect. You're wrong too. Right? These were good guesses. Right? Well, so these kids, they know they're stars, right? I'm sure you do too. But stars have got lots of elements in them. It's primarily hydrogen and helium. Hydrogen has 1 proton, right, and 1 electron, right? Helium has got 2 protons, boop, boop, and 2 electrons, boop, boop, spinning around it. The way that we make these particular very precise wavelengths of light is when things get hot and there's a lot of energy and the electron breaks free of its protons, its nucleus, and then when it falls back, it emits a very precise color of light, very precise wavelength. Problem is that hydrogen's only got 1 electron. Helium's only got 2. At these temperatures, right, 1 to 5 million degrees, those electrons are gone and their protons are not going to recapture them. So what we decided to do is to look at iron. So all of these images of the sun are made in iron. Now it's iron that has not only gotten hot enough that it's melted and become a liquid. We do that here on the Earth all the time. Not only has it become a liquid and evaporated and become a gas, right? But it's so hot right? That it's had 13, 14, 15, up to 20 of its electrons stripped away from those atoms. That takes a lot of energy. And we just can't really do that here on Earth. Right? So that's why we study the sun a lot. Now this is actually a different type of image. Right? This comes from another instrument package on the same satellite called HDMI. And the MI stands for magnetic imager. And so what we're actually looking at here are the magnetic fields in the sun. So where you see little white patches, think of magnetic fields. You've seen that picture of the Earth with like loops going around. The white is where magnetic field is puncturing the sun's surface and coming out. The black dots are where it's going back into the surface. All right? And it turns out that the magnetic field is super, super important. Because it is the magnetic field that drives everything that's going on in the corona of the sun. All those shapes, everything that you're seeing is actually driven by changing magnetic fields. Now this is one of the things I study. I try to actually put simulations in a computer so that we can try to understand what's going on here. What you're seeing is a flare going off, and the movie will cycle and repeat. But we're seeing it first here, and then here, and then here, and then here. This is the coolest channel. You have been right for this one. This is actually helium. These guys are all iron. Right? And as we watch it, we see it explode first here, and this is where we see all the energy being put into it. And then here's where it's cooling down, and you can tell it's cooling down because when it heats up, a bunch of stuff is thrown up into space. But as it gets thrown up, it expands, it cools, and it falls back down. Can you see that little guy right there? That little thing? That's Earth for scale. Yeah. So you can fit 109 Earths across the equator of the sun. You can fit over 1 million Earths inside. And this loop system right here, you could fit 5 Earths underneath it. Just to give you the scale of the types of explosions I study on a regular basis. Right? Largest explosions in the solar system, not the largest ones in the universe. That's for somebody else, but I like to keep it local. All right. So this is also fresh off of the presses today. So as we image the sun and then we combine those images with those images of the magnetic field that we make, we can actually start to trace out the magnetic fields of the sun at any given point. Right? And you see all the structure, and you remember all the loops and stuff that we saw. Those are actually lines of magnetic field. Now, if you're used to the Earth's magnetic field, right, there's a very strong north pole, right, and it goes like this. So it actually goes that way. So it goes north down to the south, like that. And it's got a very nice defined magnetic field. The sun does not. Not when it's in this active phase. It's got this 11-year cycle where it goes from active, and we're just getting off the main active track and going down to more of a quiet sun. But each one of these loops that you see here, right, actually connects a North Pole, South Pole pair. So at this part of the sun cycle, it doesn't have a magnetic north and a magnetic south. It has got literally millions of North Pole, South Pole pairs. Right? And they're constantly moving and changing. And it turns out that magnetic fields are amazingly good at generating, transmitting, storing, and releasing energy in ways that we're not used to here on Earth. And unlike other fields of science and other fields of astronomy, which have been going on since the time of Galileo, since we had to build satellites in order to see all of this on the sun, we've only really been saying this for the last 60 years. So it's very new, very fresh, and there's still a lot that we don't know and don't understand. Now, I do a lot of magnetohydrodynamics. I threatened you with equations. That's not what I'm doing right now. Right now, I am doing a lot of fun stuff. And I'm working with a lot of different museums, right, in order to bring these really beautiful, I think, images to their patrons. And so it was an exhibit. It's moving around the country now, but I did it for the Boston Children's Museum, that actually allows you to interact with these movies using a control panel. I had a lot of fun with that. I didn't design the control panel, unfortunately, but I do love it. I just provide the movies and the data. And I've also built video walls so that you can see these images next time you go to the National Air and Space Museum in Washington, D.C. Yeah, that's mine. And friends of mine are constantly sending me pictures of people sitting around, and I love it. I didn't get paid a lot for that. I volunteered most of my time. I do a lot of things for pictures of people having a good time looking at what I do. The other thing I do a lot now is data analysis. So here's a little movie of some stuff going on in the sun, right? It looks kind of interesting. There's a lot going on there. But if you actually use some really interesting math and you think about what you're trying to look at, you can actually apply that math to the images and see things that you couldn't really make out before. So this is just actually math that doesn't require anything harder than division, right? Maybe you might have to use a cosine or two. But it's thinking about the problem and what you want to image. And then you can determine things that you never would have seen before. Okay, so I'm kind of rushing through because some other speakers took a little time. I'm going to leave you with some eye candy in the background if the movie starts. So my mission's been up for 6 years now. It launched in February of 2016. Let's get that going. There we go. And I'll leave this in the background, and I'll take a couple of questions. I will tell you that one of the parts of your tour is my solar physics lab, and it's our operations center, right? I don't actually have miniature stars I keep in bottles and experiment with, right? But I do make numerical models and use observations and stuff to, in order to, oh, come on. Yeah, I thought I pressed play. Thanks for the help, bro. There we go. Yeah. So I do the computers for a living. I got my PhD in computers. Why are you not? You know what? Nope. Because you know what? No, not because Apple are better. Come on, you know this. 11, 7, 8. Yep. You know what? Fine. You want to play with me? I'll play back. Oh, well, maybe we'll leave that, and I'll let you be amazed when you come down and see the video wall. Because I was going to try to be quick. JPEG, movie. All right, well, yeah. Filter, leak. See, this is the problem when you get to do as much stuff as I do. I swear, I previewed this movie before. All right, well, sorry about that. I'll show you some, to make it up to you, I'll show you some more amazing movies when you come visit the Operations Center later on. But if you have any questions, I'll take a few, and then we'll pass on to the next speaker, because lunch has already arrived. Yep.
What causes the crazy magnetic field from the sun, and roughly on what order of magnitude is the strength of those magnetic fields?
Okay, so that's a great question. So what causes the crazy magnetic fields on the sun? Good scientific description. That is, they are actually crazy. And what is the order of magnitude? So remember that we had somebody talking about the magnetic fields in her experiment. She was talking about 4 Tesla or something. That was like the strongest magnetic fields there were, that you can make in a lab. So imagine that times about 10,000, right? So the strongest things that we can do in the lab times a factor of 10,000, right? So if I start an experiment that try to recreate those effects, not only would it levitate frogs, but everyone's compass needle would point towards my lab. And your fillings would probably be extracted from your teeth and come flying towards my lab. So we don't do that typically. And the reason why it's so crazy is that the Earth's magnetic field is constantly refreshed by a liquid iron core that's spinning. The problem with the sun is that since it's this highly conductive, very hot gas, a plasma, right? All of its layers are electrical conductors. And so you have these conductors spinning at different rates. The sun actually spins faster at the equator than it does at the pole. So at parts of the sun, it drags the magnetic field. And then further out in the corona, where I study, right, the plasma can't push the magnetic field anymore. The magnetic field pushes the plasma. So there's like a tug of war, and at this part, the plasma's winning, and at this part, the magnetic field's winning. And when they collide, things get, to use a scientific term, crazy, right? It is really hard to describe mathematically. So that's the process. Yep.
How do you compensate for the crazy magnetic fields of the sun with the telescope?
Oh, okay. That's a good question. So how do I compensate for the crazy magnetic fields of the sun? It's a telescope. I don't. The crazy magnetic fields of the sun don't affect the telescope. Because even though they're crazy on the sun's 93 million miles away. My telescope generates 3 terabytes of data a day. Does that make sense to anybody? If you think about a pretty nice home computer, it's probably got a terabyte hard drive. Fill up 3 of those suckers a day worth of data. So we put the satellite in a very special orbit around the Earth, right? And it's called a geosynchronous orbit, right? So if you go to White Sands, New Mexico, look straight up, you'll always see my satellite because it doesn't move relative to that point in the Earth. And that's because we built a big satellite dish down there that does nothing but drink from the fire hose of data that's coming down from that satellite. That it actually comes down in 1.7 terabytes a day using, again, really awesome, elegant, beautiful, yet funky math. We can compress it without losing any information. And then we uncompress it here, colorize it because it's EUV light, right? So you can't see it with your eyes. So we make it so that humans can understand it. We add colors. I hate the term false color because that makes it appear like we're lying to you. We're not. We color code it, right? It's like painting by numbers, right? And so we color code it. We analyze it. We do stuff here on this. And then all of a sudden it like balloons into 3 terabytes of data a day. So the satellite, even though it's observing the sun, it's got telescopes. It's around the Earth because if we put it further out, it'd be harder to get that much data. One more question, I think, and then we'll move on to the next. Yep. Is it true that the sun can turn into a red giant and destroy the solar system? All right, this is one of those good news, bad news things. Good news, you don't really have to worry about it. Even better news, your kids, your grandkids, your great-great-grandkids, they don't have to worry about it either. In billions of years, yes, the sun will actually go through this process, and it doesn't quite have enough mass and stuff to become a black hole or a white dwarf. And it will expand. And when it expands, right, when it changes the fuel it's using, right? So right now it's using hydrogen, right? And it's converting hydrogen into helium in a process called fusion. And that's what makes the sun bright. That's what gives us almost 99.999% of the energy on the Earth used by life. It comes from the sun in one way or the other, either directly or indirectly. So when it runs out of that fuel, it'll start burning other fuels, and when it starts burning the other fuels, yes, it'll expand. Another piece of good news, it won't expand and engulf the entire solar system. We'll kind of engulf Earth. So Earth will be gone, but this is many, many billions of years away, right? Billions of years away. You know, you might actually be my age before that happens. And so you don't have to worry about that, right? If you're worried about, things coming to an end, you're most likely to die in your bathroom, so be careful getting out of the bathtub, eat right, jog, don't smoke. These are the things you need to worry about. You don't really need to worry about yes, it will happen. It's billions of years from now, and I'm working on it. So. All right, so, okay, well, quick question, and then I'll answer questions when we do the tours.
You talked about the electrons coming out of.
Yeah.
What happens to the chemical composition?
No. Chemical composition is the same. So, the electrons usually want to be in this nice orbit around the protons. But when they get too energized, right, they go off, but they don't go flying off in space. They're just like bouncing around, having a good time, right? They're just not bound by the proton anymore, right? So the proton's still there, and the electron's still there, but it's just not making that nice circular pattern, right? And so that's what the process called ionization, right? And when you talk about chemical composition, right, you're actually just talking about those protons and neutrons, right? And all right, so those actually stay the same, except in the core, right? It's really just in the core of the sun, the bowels of the sun, the reactor of the sun, where the chemical composition changes, and that changes because it's so hot, there's so much pressure, so much gravity that two protons are getting pushed together, or two hydrogen atoms are getting pushed together, and creating helium, which is the other major component of stars. So the chemical composition only changes actually in the core of stars, or when the stars go through a process of exploding at the end of their lives and dying, called supernova. Okay? All right. Well, great. I will talk more, and we'll have working movies on the tour.